So folks, in the previous video, we showed where this particular equation of the tangent plane came from. So if you have any questions on that, jump back to that video. I want to remind you of what we thought of the tangent plane as. It was, in our construction on the previous page, it was the collection of all tangent vectors of all curves passing through that point on the surface. And at the end of this video, I'm going to give you one other way of thinking about the tangent plane. But again, this is our current working definition for the tangent plane, or working formula for it, but we're going to develop a second one. And we've already discussed in the pre-work videos why it's important to have these two different definitions. Sometimes it's easier to discuss a function explicitly, other times it's easier to work with the function implicitly, but we want to show that these two definitions are compatible with one another. So let's go ahead and do so. Let's start out with the function z is equal to f of x, y. And what we've done a few times before is let's create this, take this explicit function and make it an implicit level surface. So to do so, let's subtract over the f of x, y, setting it equal to 0. And this is what we're going to call our f of x, y, z. So now we have a function f of x, y, z set equal to 0 describing a surface. And, oh, I forgot to add, we need to let c be the value when we plug ab into this function. So we've got the point ab where we want to construct the tangent plane on our surface. If we plug ab into the function, it outputs some value c. So using this formula, at the point ab, f of ab, which is the same thing as the point A, B, C, we know using that formula that the tangent plane is f sub x of A, B, C times x minus a plus f sub y of A, B, C times y minus b plus f sub z of A, B, C times z minus c needs to equal 0. That's using this tangent plane. I went ahead and did the dot product in my head, but that's that formula. Okay, well, so we need to compute f sub x, we need to compute f sub y, we need to compute f sub z. So notice that f sub x would just be the partial derivative of this expression right here with respect to the variable x. Well, when I take the partial derivative of the independent variable, remember when we do this as an implicit surface, z is treated as independent. When I take the partial derivative of the independent variable z with respect to x, I just get 0. And then I would have minus, because the negative sign factors out, and then the partial derivative of this with respect to x, f sub x of xy. Likewise, if I were to compute f sub y, I would get 0 minus f sub y of xy, and then if I compute f sub z, and this is, to me, this is why this suddenly appears to work, is when we take the partial derivative of this expression with respect to the independent variable z, this function, this entire second term, its derivative is 0, and we just get 1. So if we were to evaluate f sub x at the point a, b, c, everywhere I see an x, I'll plug in a, everywhere I see a y, I'll plug in b, and everywhere I see a z, I'll plug in c, but that just gives me minus f sub x of ab. Likewise, if I do the same thing here, f sub y of abc is just going to be minus f sub y of ab. And then f sub z of abc, I guess, is the easiest of them all to evaluate. Everywhere I see an x, I plug in a. Everywhere I see a y, I plug in b. And everywhere I see a z, I plug in c, but there's nothing to plug in, so we just get 1. So then we just plug these values into our equation of the tangent plane, and so I get minus f sub x of ab times x minus a minus f sub y of ab times y minus b plus 1 times z minus c equals 0. So the first thing I'm going to do is, since I'm only got one line room left, I'm going to replace this c back with f of ab when I work with this. Then what I'm going to do is I'm going to take this term over to the other side, this term over to the other side. I'll distribute this 1 through, which is really trivial, and then I'll add this over to the other side as well. So when I do so, I end up with z is equal to positive s of x, evaluated ab, times x minus a, plus f's of y, evaluated ab, times y minus b. And then there's the z, which I've left on this side, and we have this minus c, which I'll add over. So I would add it over as c, but remember that c is just f of ab. And there we have the alternate equation of the tangent plane, which is what we saw in our pre-work. So folks, the last thing I want to show you about deriving these formulas is something we could have done from the get-go, but it wouldn't have enabled us to come up with both equations of the tangent plane. But let's say we had some surface, and I want to show you another way of thinking about what the tangent plane is. So let's say we had this surface here, here's z, here's x, here's y, we said that was z, and so if I take some point on the function, which let's see here, let's go up here and label it, we'll just put the point on the function, but that maybe corresponds to this domain point down here. If I were to, in the domain, step in the positive x direction, and look at what that, so notice from there, once I've got that, I can go ahead and find another point on the surface, and I can create a trace through my surface here. And remember that this this vector, this is the direction vector 1, 0 that I just stepped in, because I stepped in the positive x and I didn't allow y to change. Well, this vector simply computes the partial, I mean, we could use this vector to help us compute the partial derivative of f with respect to x. And if we did so, we would come up with this vector right here. Let me put it in purple. It's going to get a little bit cluttered. With that vector right there, which is a vector that's tangent to the surface, but specifically along this purple curve here. And that vector would be the vector, we get the first coordinate 1 from that coordinate vector, the second coordinate would be 0, and the third coordinate would be the directional derivative that we evaluate at that point, but that would just be f sub x of ab. Why is it f sub x? Because the directional derivative, the direction we're heading in, is just in the positive x direction, so computing the directional derivative there is the same as computing the partial derivative of f with respect to x. Likewise, we could from that point look in this direction. And if we looked in this direction, let me make that a little bit better. There we go. If we looked in this direction, this would be the direction 0, 1. And so we could take a trace slice through our surface, would look something like this. It should look familiar to the pre-work videos that you did in the directional derivative section. And if we did that, then we could come up with this tangent vector right here, where this tangent vector right here says we're going to step 0 in the x direction, 1 in the y direction, and then ask the question, as we do so, how do our z values change? And the answer to that would be just the directional derivative in the direction 0, 1 at the point AB for our function. But folks, what I'm telling you is that this is the same thing as just computing f sub y of AB. Okay? So I'm going to replace that here. So another way to think about the tangent plane is go to the point in your domain and look in all possible directions that you could possibly leave from that point. And compute then all of those corresponding directional derivative vectors where you get the z coordinates of the vector from the directional derivative. That whole collection of vectors then gives you your tangent plane. So that's another way to think about it. Now, why is that beneficial? Well, another way to talk about this then is we've got this vector right here, which would be the normal vector. And forget about what we've done recently. How did we used to find the normal vector of a plane? Well, we would take two vectors that we knew to be in the plane. Maybe we call this one v1, and maybe we call this one v2. We take two vectors that we knew to be in the plane, and we do what to compute the normal vector? We would compute the normal vector by taking v1, crossing it with v2. And if we were to set up that cross product, you would just have I, j, k, and then v1 is the vector 1, 0, f sub x. I'll just write f sub x and I'll leave the a, b off till the end. And the v2 is this vector right here, which is 0, 1, f sub y. And if I compute that cross product, folks, what I end up with is just, and I'll stop worrying about the colors here, I end up with just minus f sub x I hat minus f sub y j hat plus 1 k hat. But notice that that's precisely the vector that I had for the normal vector here. Minus f sub x, minus f sub y, and 1, which is another way of seeing how we could get these normal, the n1, n2, and there would be the n3 for this normal vector to this tangent plane. So folks, I wanted to show this to you because I think it's a valuable insight to say, hey, we could go to a point on a surface and in the domain look in every possible direction. Every single one of those will give us a vector whose z-coordinate is determined by the directional derivative, and the collection of those vectors gives us a tangent plane. That's a slightly different perspective than what we had up here, where we talked about curves passing through, any collection of curves passing through the point of interest, and then computing the tangent vector to the curve, and then constructing the plane that way. So it's a slightly different way of thinking about it. Both viewpoints are valid, but the order that we did this in was the necessary order, I think, to be able to come up with both equations. Let me know if you have any questions on that, and I hope you found this helpful.